Yes, we can hear you.
Very good. Good morning from Hamburg. Should I just share my slides and go ahead?
Yes, please do go ahead. And people, you can put questions into the chat as they go along, or we can have questions at the end.
Mm-hmm. Let's see if this. So okay. So you see my slides? Okay.
Yes.
So the title is DESY, the decoding of matter. A little bit of history, something about the present at DESY, and also something about the future. My name is Ulrich Husemann. I'm the director of particle physics at DESY. So here's just a brief introduction of myself. I studied physics in Germany, in Dortmund, in fact, and then got my PhD on an experiment that used to be at DESY with the name HERA-B. Then I moved on to the US, being a postdoc at the CDF experiment at Fermilab. That is was a big collider experiment. And then I moved on back to Germany, back to DESY. In fact, to the other side, not the Hamburg side. I'll tell you about that in a minute. Where I worked on the Atlas experiment, like Kate does. And then I moved as a professor of particle physics to Karlsruhe Institute of Technology. That's also in Germany, the southern part. And I switched experiments and worked on CMS ever since. And since this month, I'm the new director of particle physics at DESY. So I'm rather new to DESY, but also not, because I've been here before. So I may not be able to answer you every detail about DESY, but I'll certainly give it a try. In terms of my own research, I've been dealing a lot with the physics of the pop quark, the heaviest known elementary particle, and the Higgs boson and how they play with each other. And I also like building detectors, and this is mainly semiconductor detectors for tracking in our field. So you see me here in front of our test beam at DESY. All right. So the decoding of matter goes over many orders of magnitude in scale, starting from a galaxy and ending up with quarks, which, according to our knowledge of today, are point-like particles. And at DESY we cover a lot of this part here. So if you look at the galaxy and its evolution, you may ask, what does particle physics have to do with this? The particles and forces of the universe, how do they influence how the universe evolves? And what is this elusive form of matter that we don't know about that is called dark matter? But we can also move to other scales. A virus is much bigger than much smaller than a galaxy, but much bigger than an elementary particle. And this is also something we address at DESY, which is not my field of expertise. For instance, understanding infection on molecular levels or controlling the functions of materials on the level of electrons and spins. And then this is more my realm, the question of the origin of the fundamental forces that we know of, the strong force, the weak force, and the electromagnetic force and gravity. And then the mechanism that gives mass to particles. We know there's the Higgs boson. I'll talk about the Higgs boson a bit, and how this all fits together. So at DESY, we basically try to cover lots of these things. And we do that by using particle accelerators, powerful lasers, computers, and detectors. And as I said, my personal preference is in detectors mainly. Right, and the research questions you can ask here is how do you build an accelerator that is much smaller than the huge things that are there all over the world where you accelerate particles, or also how do we build a detector that can take millions of pictures in a second, and how do we process the data that comes out? These are all important questions in moving forward in physics. So where is DESY? So here's a world map. Here's Afghanistan. Here's Germany. So it's a small country in Central Europe, about 80 million inhabitants. And if we zoom in, Hamburg is in the northern part, and the other side of Zeuthen is Teuthen, that is close to Berlin in the eastern part. So DESY is the name stands for German Electron Synchrotron, and that goes back to the history of DESY. It was founded as Germany's national lab for accelerator physics. And as I said, there's 2 locations in Hamburg and Zeuthen. The Zeuthen site is the newer one. This merger happened after German unification in the early 90s. It's a fairly big lab. We have around 3,000 employees. That includes scientists, but also engineers, technicians, administrative staff. And we also have visitors, about as many per year, and a budget of about 300 million euros a year. This is copied from our mission. We conduct top-level international research, and we offer young researchers, and this is relevant for you, an international and interdisciplinary setting on ambitious scientific projects. So how did it all start? This is an aerial view of DESY in its very beginning. I'm somewhere behind this hill here on that side. And this is the first accelerator that has been built in the late 50s or started. And that was called DESY, and that's the namesake of the lab. DESY is this small thing here, and this is a view today where particle acceleration starts from a LINAC, a small booster called PIA, and the DESY ring that I just mentioned. But then there's also a ring that has been dismantled by now, that was called DORIS, that was also significant for particle physics. And then there's the bigger ring that is still in operation today. It's called PETRA. It used to be a particle physics-driven collider, E plus E minus collider, and it's now used, as you can see from the big hall in front here, for synchrotron radiation. There's synchrotron radiation beamlines here. There used to be an even bigger accelerator called HERA. This is where I did my diploma and my PhD. That went into operation in 1991 and looked at the structure of the proton, basically. And then there is new accelerators that have been built in the 2000s. They are basically X-ray generators by means of a free electron laser. So with electrons, you can generate lasing effects that are in soft X-ray for this kind of machine. And then there is the European XFEL, which is operated by DESY, but is its own entity. That's a 3-kilometer LINAC that accelerates electrons that can then also be used for X-rays. And I see a hand open. So should we take questions in between? If there's immediate questions, I'm open to that. So please go ahead.
Lorman, you raised your...
There's
maybe they raised their hand by mistake. We just can't even.
Okay. All right. Then I just continue. So as you saw, we operate large-scale infrastructures. I just talked about PETRA, the second biggest accelerator built here. PETRA 3 is the third incarnation of that device. Is the world's largest synchrotron radiation source. I also talked about FLASH, the world's first free electron laser, and the European XFEL, which is an X-ray laser and a huge device. Then we have large data and compute centers to process all the data. I showed you a picture of the test beam facilities already, with me standing in front of it. We have 300 to 400 users each year coming, testing their new detector devices with actual beams. That's mainly a service for particle physics and related communities like nuclear physics. And there's several interdisciplinary centers on campus, on theoretical physics, on various things around these X-ray beam lines, which I'm still learning. As I said, I'm new to DESY. The next big future project is called Petra 4, Petra 4, Petra 4 in German. So that's the fourth incarnation of Petra. And that's an upgrade of Petra 3, 500 times more powerful in some metric. I think it's brilliance for X-ray light sources. The construction is planned for 2029 and will have a broad range of application for all sorts of fields, from drug development in the medical realm to microelectronics. You can basically X-ray your microelectronics or nanoelectronics even, developing materials and material science and many, many more. So this is the big project that we have ahead of us at DESY. But we also have some research history, more from my field, from particle physics. One thing that was a highlight, and that also happened at Petra, was the discovery of the gluon. That's the particle that mediates the strong force. And if you ever seen Feynman diagrams before, you have an E+ E- annihilation into a virtual photon, and then you have three particles going out, a quark, an antiquark, and a gluon. And in the detector, it looks like this, and this has been first seen at DESY. And moving on from that, DESY studied the structure of the proton with unprecedented precision. What you see here on the right-hand side is basically the unification of forces as a function of the momentum transfer in deep inelastic scattering. I don't have time to go into the physics, but feel free to ask me questions later. So this is the legacy of the Hera collider. This is another field. This is from basically biology, where we have managed to look at the structure of complicated molecules in human cells, which brought a Nobel Prize for Ada Jonat, who did these studies in the 80s. And here's some pictures from new accelerators. In the middle, this is the accelerating structure that has been developed for the European XFEL. It's a niobium radio frequency cavity, and these are the devices that basically push the particles into higher energies when you accelerate particles in a linear accelerator. So let's come a little bit more closer to my field. What do we do in terms of particle and astroparticle physics? The basic goal is to understand what our universe is made of on the fundamental level and how this influences the evolution of the universe. So if you start from the Big Bang, like 14 billion years ago, and move all the way to today, you can have a time line here, but you can also draw an energy scale here. And the idea is that after the Big Bang, the universe cooled down, and basically during the various phases, several things happened, like the forces of nature separated, nucleons formed, and then atoms formed. This is basically the point where the universe became transparent. And then we have the first stars, and at some point we are today, and have to work our way backwards in understanding what happened. Now, how do we do this? In astroparticle physics, the current trend is called multi-messenger astronomy. This is also pursued at DESY. So suppose you have something that emits cosmic rays. That could be, for instance, a black hole in the center of a galaxy. And it emits all sorts of particles. It emits neutrinos that go straight through Earth. It emits gamma rays, and also emits charged particles like protons and heavier elements. And they all eventually end up on Earth. And DESY contributes to experiments both on satellites and on the ground, looking for gamma rays. There's a big experiment at the South Pole that's called IceCube, where DESY is also a major player in looking at neutrinos at the South Pole. Also on top, you see this array here is also suited to detect cosmic ray charged particles that give you a shower of particles in the upper atmosphere. By the way, this on the bottom, this is the galactic plane as viewed in TeV photons by the Hess experiment. Then this is more my field. We're in a collider-based particle physics where we are involved in external experiments. So this is not on DESY side, but this is now CERN. You'll learn a lot more about CERN later on. This is the LHC is a big particle collider, the biggest in the world, 27-kilometer circumference, about 100 meters underground. And DESY is in both big experiments here, ATLAS and CMS. You see a picture of the ATLAS detector here, cutaway view. So the particles collide here in the middle, and then you have dedicated instrumentation to measure momentum, energy, and which particle has which particle is which, basically, to distinguish the type of particle. In addition to collider physics at the LHC, we are also part of an experiment in Japan that's called BEL-2. The detector looks fairly similar, but of course, in detail, it's very different. This is an asymmetric E plus E minus collider for flavor physics. So these two approaches are complementary. This is why we are in both at the collider and at the more specialized so-called B factory in Japan. This you might have seen. This is the other big experiment at the LHC, what is called an event display. So the collision of two protons happens here in the middle, and then many particles come out, and you see their trajectories here. And there's two particles which deposit energy here, basically back to back. You can immediately see this. These are two high energetic photons, and if you reconstruct the energy, you can infer from that they must have come very likely from a Higgs boson decaying into photons. So DESY scientists were at the forefront when this breakthrough happens at CERN in 2012, and I mean, this is still unfolding. We're still learning every day. We are learning much more about the Higgs boson and how it interacts with the rest of the world. And the Nobel Prize wasn't for the discovery, but for the theoretical prediction. But anyway, we feel honored that this was made possible by the Nobel Committee also. At DESY, we also have an on-site program in particle physics. And just going through quickly, I just dropped some names and ideas here. The basic idea is that there may be very light particles that make up the dark matter and may have other ramifications in nature. They're called axion light particles. There's various ways of searching for them. You can take a big laser and see if you can shine through a wall with the laser. That only works if the laser light is converted into these light particles and converted back afterwards. That's the ALPS experiment. It's taking data. You can also look at the sun and see if these particles actually come from the sun. So you basically, that's called a helioscope. So like a telescope that points at the sun, you know, and then you see what comes there. And again, you take a strong magnetic field and try to convert these light particles, these axions from the sun, into something you can detect. Another way is to assume that there's dark matter all around us in the galaxy. And to show that, you build haloscopes. So in the halo of the galaxy, that's hence the name, there might be these axion dark matter particles. And here's an experiment to do this that is being prepared. And the fourth one doesn't have anything to do with axions, but is a strong field QED. QED stands for quantum electrodynamics. That's one of the fundamental theories of particle physics, the best tested theory ever, I think. And it's being studied under extreme conditions where there still may be surprises. This is also an experiment in preparation at this point. Right, before I close, let me just advertise one thing. DESY has a summer student program that invites up to 100 students of physics and related disciplines over the summer for 7.5 weeks. They are embedded in our research projects, on-site or off-site. And there's a dedicated lecture series for all of them. This is meant for students who finished their bachelor's degree in the European system or equivalent. So that means 3 or more years of full-time university level studies. The new call isn't quite out yet, but there will be a summer student program next year. And the deadline is probably somewhere end of January. So with that, I hope I could give you a small insight into what DESY is and what research at DESY can do. And I'm looking forward to your questions.
Thank you very much, Ulrich. It was very nice talk. If you have any question, please unmute yourself. We don't have much time, maybe 1 or 2 questions we can ask if you have.
So there was one question in the chat, can students from Afghanistan also apply? There's no restriction on the nationality, as far as I know. So we regularly have people from all over the world.
Okay, it seems there is no question. Thank you very much, Ulrich, for the presentation. It was very nice, and I hope students can benefit from this program, and those who are interested, they can find the email and contact of the Professor Husemann on their materials that we upload later in ICTP Indigo page. Thank you very much.
There is a question,
Welcome.
I think. There is
Yes,
there's
is this question? Okay, we'll take that one.
Muhammad Rahim wants to ask a question. You can unmute yourself. I think maybe.
Okay, thanks. Thank you for your beneficial description of the summer student program. I have a question about should the students must be masters or just bachelor of physics?
As I said, the typical thing in the European system is that you have a 3-year bachelor's and then a 2-year master's. So younger than that doesn't usually make much sense. It may happen in exceptional situations, but it's typically people who just started their master's or after their bachelor's.
Mm-hmm. Okay, thanks.
Okay, thank you very much. I think, yes. Any question? Okay. Thank you very much, Ulrich, for your presentation. And we are now going to our next speaker. And so for the next speaker, we have Professor Antonio Cattaneo from EBRI. I'm very happy to have him here and very happy to accept it to give a presentation of the European Research Institute, Rita Levi-Montalcini, where I am doing my research here. EBRI was very supportive and encouraging the programs we had here. Also for the machine learning workshop, we had their support able to organize this 3-day workshop for the artificial intelligence for Afghan students. Now we have him here give a talk about EBRI and hi Antonino.
Hi Zainab, hi Kate, hi everyone. Let me just try to share the screen. Is always a challenge. Can you see it? Well, see it coming. No, I cannot see it myself. No. I'll try it again. Sorry. It's always